Welcome to The Explainer. Today, we're going on a fantastic voyage, literally shrinking down to follow a single beam of light through the complete instrumentation of an atomic absorption spectroscopy, or AAS, machine. Dr. Kem broke this down beautifully, and we're going to walk through the entire setup from start to finish.
All right, let's jump right in. The core principle of AAS is actually pretty elegant. It all relies on free, neutral atoms absorbing very specific wavelengths of light in the gaseous phase. Think of it like an optical fingerprint for every element. By shining the exact wavelength of light that a specific target metal loves to absorb through a vaporized sample, we can spot trace metals that are completely invisible. We're talking about finding a single drop of poison in an Olympic-sized swimming pool.
But here's the kicker. We don't just want to know if an element is there. We need to know exactly how much of it is there. Enter the golden rule, the Beer-Lambert law. It's kind of like putting on sunglasses. The thicker the lenses, or in our setup, the more analyte atoms floating in that optical path, the more light gets absorbed. It's a direct, perfectly proportional relationship that gives us an incredibly precise way to measure concentration.
So, here's our mental blueprint for today's journey. First, radiation sources. Second, sample introduction and atomizers. Third, the monochromator and detector. And finally, the signal processor and readout.
Let's kick things off with step 1, radiation sources. This is where our light beam is born. The hollow cathode lamp, or HCl, is the absolute standard workhorse in conventional AAS. Now, here's what's so cool about it. To find a specific metal, let's say lead, you actually use a lamp that contains a cathode made out of lead. When you energize it, it emits the exact sharp, characteristic wavelengths that ground-state lead atoms will absorb. It's basically a perfectly matched tuning fork for your target element. But, some elements are just stubborn. They're much harder to excite. That's exactly where the electrodeless discharge lamp, or EDL, steps in. Instead of a standard cathode, it uses radio frequencies to excite the atoms, which pumps out much stronger emission intensities. It's a lifesaver when you're dealing with tricky elements, requiring higher radiation intensity to get a solid signal. Moving right along to step 2, sample introduction and atomizers. So, our perfectly tuned light beam is on its way, but we obviously can't just pour our liquid sample straight into the light path. First, the sample introduction system uses a nebulizer to suck up the liquid and shatter it into fine aerosol droplets. Then it hits the spray chamber. This chamber has baffles that act like a physical bouncer, stripping away the larger droplets and sending them to waste. This guarantees that only the absolute finest, most uniform mist actually makes it forward into the heat.
And Dr. Kem made a point to emphasize this. The atomizer is literally the most critical component of the entire AAS instrument. Its one and only job is to efficiently convert your sample into free ground-state atoms. If it doesn't do that properly, those atoms won't absorb the light from our lamp, and your sensitivity just completely tanks. Look at this split-second, incredibly violent physical transformation. The aerosol mist hits the heat and instantly undergoes desolvation. The solvent basically boils right off, leaving solid microcrystals. Then, boom, volatilization turns it into a gas. And finally, rapid dissociation breaks it down into the free, neutral ground state atoms we desperately need to measure. And we have to catch them right then, before they get too excited and become ionized. For your standard, routine metal analysis, the flame atomizer, or FOSS, is your go-to. It usually runs on an air acetylene or nitrous oxide acetylene flame, sitting right on top of a laminar flow burner head. Now, the brilliant part of this design is that it creates a flat, ribbon-shaped flame. This gives our light beam a really long, quiet optical path, maximizing the odds that the light will actually strike our target atoms as they fly through.
But what if you need extreme sensitivity? Then you bring in the graphite furnace atomizer, or GFAS. Here, a tiny, discrete drop of sample gets injected into an electrically heated graphite tube. Instead of a continuous flame, it runs a highly programmed thermal cycle. It dries at around 110 degrees, ashes up to 1,000 degrees to burn off the matrix, and then, bam, a massive, rapid spike all the way to 3,000 degrees for atomization, followed by a final 3,500-degree blast just to clean it out.
When you compare the two side by side, it really all comes down to atomization efficiency. With the continuous flame, you're only getting about 5 to 15% of your sample into the flame. But the graphite furnace, it traps the entire sample in the optical path, achieving near 100% efficiency. This is what unlocks ultra-low trace analysis, dropping our detection limits from parts per million all the way down to parts per billion or even parts per trillion.
All right, phase 3, the Monochromator and Detector.
So our light beam has survived the intense heat of the atomizer, but now it's mixed with a ton of chaotic background radiation from the flame. We need to filter it. The monochromator is essentially the instrument's VIP bouncer. It uses an entrance slit, a prism or diffraction grating to split the incoming light into a spectrum, and then a super precise exit slit. This setup isolates only our specific analytical wavelength and blocks out all the wanted optical noise.
Once we have that perfectly isolated beam, it strikes the detector, which is usually a photomultiplier tube, or PMT. Remember, absorption means the light intensity has decreased, so the PMT has to act as a massive amplifier. It catches those surviving photons, strikes a cathode, and triggers a cascading multiplication of electrons. It literally turns a tiny drop of light into a highly measurable electrical signal.
And finally, step 4, the signal processor and readout.
This is the grand finale of our fantastic voyage. The signal processor catches that amplified electrical pulse from the PMT and crunches the numbers. It converts the raw transmittance data into an absorbance value based entirely on that Beer-Lambert law we talked about at the start. That perfectly proportional number gets pushed right to your digital screen, handing you the exact concentration of your sample.
And there it is, the complete 6-step sequence of this incredible technology working in split-second harmony. From the light source to the nebulizer creating the aerosol, the atomizer doing the heavy lifting, the monochromator filtering the noise, the detector capturing the signal, and finally the readout system displaying the results.
It's honestly mind-blowing how we can harness fire, electricity, and the fundamental properties of atoms to decode the microscopic world. So, now that you know the intricate journey required to look for the invisible, what trace elements are you going to uncover in your next sample? Stay curious, and we'll catch you on the next explainer.